Welcome back to the deep dive. Today we're going to cut through some of the noise in parameter-efficient fine-tuning, or PAFT, and really analyze a method that looks to bridge the gap between efficiency and, well, full-scale adaptation in LLMs.
That's right. Our source material is the 2023 paper from Wang and his colleagues, MultiLoRA, Democratizing LoRa for Better Multitask Learning.
And our mission here is to get to the bottom of how this new method, MultiLoRA, actually solves some of the, inherent structural limits of standard LoRa.
Especially when you're trying to scale up to these really complex, diverse multitask scenarios.
Okay, so let's set the stage for you. The whole context here is that LLMs, particularly models like Llama, have just gotten so good.
Right, they've delivered incredible performance, and everyone's chasing this dream of, one model to do everything.
That one model for all tasks vision is so appealing, but the traditional way to get there, full parameter fine-tuning, or FT, it's just so expensive.
It's prohibitively expensive. The hardware costs are immense. We're talking about just the memory for optimizer states and cache data for a model like Llama 65B it's out of reach for most.
And that's exactly why PEFT methods, and specifically LoRa, became so popular.
Oh, absolutely. LoRa is a brilliant piece of engineering. It's resource efficient, the modules are easy to distribute, and you can merge the weights back in so there's zero inference overhead. It's elegant.
It's been a game changer for single task fine-tuning, but that brings us to the core question this paper asks.
Which is, can LoRa really perform as well as full fine-tuning when things get complicated? When you have a really messy multitask problem?
And the authors argue, pretty convincingly, that no, it can't. That the explicit low-rank design of standard LoRa is actually a bottleneck.
It is. It limits the model's expressive capacity. So the solution they propose is MultiLoRa. The whole idea is to democratize the underlying transforms to get past that limitation.
Okay, democratize. Let's unpack that. The paper uses this really foundational diagnostic tool to show the problem, right? Singular value decomposition, SVD.
Yes, the SVD analysis of the weight update matrices, the delta W words, is really the heart of their argument. It shows you exactly what's going on under the hood.
So what does it show? What's the difference between the update matrix for LoRa versus full fine-tuning?
Well, when you look at the matrix from full fine-tuning, delta WFT, the singular values have this nice spread-out distribution, a bell curve, basically.
Meaning the importance is spread across many different components.
Exactly. The energy of the update is distributed across a large number of unitary transforms. The authors have a great name for it. They call it a democratic composition.
I like that. So democratic. What does the LoRa update matrix look like then?
It's the complete opposite. You get this extreme bimodal distribution. All the energy is concentrated in just a few places.
Which means the update is relying almost entirely on a tiny set of top singular vectors.
Precisely. The rank constraint, the dollars in LoRa, forces the update to be composed of only a few dominant transforms. It's like if full fine-tuning is a diversified portfolio.
Okay.
Standard LoRa is putting all of its money on one or two high-risk stocks.
And that makes sense. So if you're in a multitask setting,
Yeah.
let's say instruction following and arithmetic and world knowledge.
All at once.
Right, all at once. You need the model to learn very different things. But if you're constrained to just a few of these dominant pathways, you're going to have problems. You risk catastrophic interference
Or you just fail to learn the less dominant tasks.
Yeah.
The top vectors just steamroll the whole learning process. There isn't enough capacity left to fit the more subtle changes needed for other tasks. That's the structural insight that really motivates the whole MultiLoRa redesign.
Okay, so that's the problem. Let's get to the solution. The goal is to make the MultiLoRa weight update matrix look more like the democratic one from full fine-tuning. How do they do it?
They make three major changes to the design. The first one is what they call horizontal scaling.
So instead of one big LoRa module,
You use two smaller LoRa modules in parallel. You're effectively breaking down the final activation change, delta Y or Y, into a sum of contributions from independent parts.
I want to push on that a bit. If the final update is just the sum of these LoRa matrices, how does that fundamentally change the singular value distribution? Doesn't the rank just add up?
That's a great question, and it's subtle. The real gain isn't just about the theoretical maximum rank. It's about increasing the degrees of freedom for the optimizer.
Ah, okay.
By creating nowhere independent paths, you reduce the dependency between the parameters in those up projection matrices, the lie ball matrices. It gives the optimizer a much larger, more flexible search space to find a balanced solution for the final sum delta MOA.
More pathways means less reliance on a single dominant path.
Got it. Okay, what's the second change?
The second is about parameter initialization. Standard LoRa usually initializes one of its matrices with all zeros to make sure the initial change is zero.
Right, for stability. But MultiLoRA breaks with that. They initialize the up-projection matrix by $a level using Yiming uniform initialization.
Which is a pretty standard but non-zero initialization. Why do that?
It's a powerful move to boost expressiveness right from the start. Initializing with zeros is stable, sure, but it's also very constraining. You can introduce redundancies. By using Yiming, they're kind of preceding the adaptation with a more diverse starting point, letting it learn distinct features much faster.
But wait, if they're not using zero initialization on byte-lollers, how do they maintain that crucial stability? How do they keep the initial activation change at zero?
And that is the third clever bit of design. They introduce learnable scaling factors, one for each parallel module.
Okay.
These scaling factors, they call them scaling collada, are themselves initialized to zero. So since they multiply the output of each module, the total output delta will 1 is 0 at the start of training.
So you get the best of both worlds. The expressiveness from the Yiming initialization on B, but the stability from the zero initialized scalars.
Exactly. The parallelism, the Yiming in it, and the scaling factors all work together to create this much less constrained optimization, pushing the update matrix toward that democratic ideal of full fine-tuning.
Makes sense. So let's talk about how they tested this. A good theory is one thing, but you need rigorous experiments. They put together a pretty brutal training data set, didn't they?
Oh yeah, they specifically designed it to stress the model's multitask capabilities.
It's a mix of tasks with really different semantic and syntactic structures. You've got instruction following with alpaca,
World knowledge from MMLU, complex arithmetic reasoning with GSM-8K.
and then a whole bunch of natural language understanding tasks from Super GLUE. So it's a really diverse, challenging mix.
And their baselines were solid. They used the whole llama family, 7B up to 65B. And they compared against not just full fine-tuning, but a very strong standard LoRa baseline.
What do you mean by strong?
They put LoRa modules on every single linear layer. The query, key, value, output projections,
Yeah.
everything. So they're making sure MultiLoRA isn't just beating some weak toy implementation of LoRa.
And I thought their evaluation method was interesting. They didn't just cherry pick the best score for each task.
No, and this is so important for multitasking. They reported the task scores at the point where the best average score across all benchmarks was achieved.
Which forces the model to be good at everything at once, not just sacrifice one task for another.
Exactly. It's a true test of holistic performance.
So let's get to the results. Did the democratization strategy actually work?
It did, unequivocally. MultiLoRA consistently and significantly outperformed standard LoRa.
Give me an example.
Okay, for the Llama 7B model, they compared MultiLoRA with 3 parallel modules to a standard LoRa, and they kept the parameter budget identical, just about 3.6% extra parameters over the base model.
And the performance.
MultiLoRA delivered a 3.5% improvement on MMLU and a massive 5.9% improvement on the RTE task. Across the board, it beat the strong LoRa baseline by almost 3% on the average score.
That's a big deal. And what about stability? That was part of the hypothesis.
Yes, and that was confirmed too. MultiLoRA showed really small performance fluctuations, much more like full fine-tuning. Standard LoRa, on the other hand, was much more volatile. You'd see swings of over 3% on some of the tasks. So the balanced approach really does lead to more reliable adaptation.
Now here's the result that really jumped out at me. MultiLoRA didn't just match full fine-tuning on the smaller models, it actually beat it.
Right. On the 7B and 13B Llama models, it actually outperformed FT. We're talking about a 1.1% average score improvement over full fine-tuning on Llama 7B.
That feels counterintuitive. How can a method that updates fewer parameters get a better result than one that updates everything?
Well, the paper suggests that for these smaller models on diverse tasks, the structured approach of MultiLoRA acts as a kind of helpful regularizer. It might be guiding the optimizer away from poor local optimizer that the huge, unconstrained search space of full fine-tuning could fall into.
It's guiding the optimization into a better, more structured subspace.
That's fascinating. Okay, so we have significant, stable performance gains. But what's the cost? What about the GPU resources? Well, the good news is on throughput. Because it's so parallel, training throughput stays really high. For Llama 7B, it's around 400 tokens per GPU per second.
And how does that compare to full fine-tuning?
It's nearly double. FT was only getting about 208 tokens per GPU per second, so it maintains that core efficiency benefit of PEF.
That's the good news. I sense there's some bad news coming. What's the trade-off?
The trade-off is memory. VRAM. The
Ah.
VRAM usage scales linearly with $5, the number of parallel modules. And that's because each module needs its own cache for activations.
So for you, the practitioner, that means if you use a high dollar, say 5 parallel modules on a long sequence.
Your VRAM usage can actually be higher than it would be for full parameter fine-tuning.
Wow. That is a critical limitation, especially for any kind of industrial application with long context windows where you're already fighting for every megabyte of VRAM.
It's the primary constraint of the method. The performance is there, but you have to manage the memory penalty very carefully.
Okay, let's close the loop and go back to the SVD analysis. Did they confirm that these performance gains were actually caused by the democratization mechanism they designed?
They did. They went back and analyzed the final MultiLoRA weights. And using a measure of subspace similarity, they confirmed that the space explored by MultiLoRA's update was significantly closer to the one explored by full fine-tuning.
So it was learning in the same neighborhood as full fine-tuning, which LoRa wasn't.
Exactly. And the real smoking gun was looking at the singular value distribution again.
And it looked like the bell curve.
It did. It now mirrored that democratic bell-shaped curve of FT. The influence was diffused away from just a few dominant vectors. They successfully balanced the contributions.
Meaning that by increasing no dollar the number of parallel modules, you're able to amplify features at a much more fine-grained level.
Yes, you get more of those small singular values, which lets you fit the details of the weight update matrix much more accurately, just like full fine-tuning does.
Okay, so to recap this deep dive, MultiLoRA seems to be a really novel and powerful solution to the multitasking limits of standard LoRa.
It is. It uses this structured parallelism and some clever initialization tricks to get more stable and superior performance, even beating full fine-tuning on smaller models.
And all with a pretty minimal parameter overhead.
Right, and that really brings us to the final thought for you as an engineer trying to apply this work. We know MultiLoRA's main drawback is that linear scaling of VRAM with the number of parallel modules, $9.
Right.
So given that hard constraint, the big question is, how do you systematically figure out the optimal value for $9? How do you find that perfect balance that maximizes the performance gain you get from democratization without completely blowing your VRAM budget, especially in a production setting with long sequences?
The optimization problem is no longer just about the performance metrics, it's about the resources too.
Exactly. It's a resource-aware optimization problem.
A fascinating challenge that really defines where efficient LLM deployment is headed. Thank you for joining us on the deep dive.